Okay, so what we have is we're looking at temperature, and we know as the temperature increases, then what happens, the particles move faster and faster. Okay? Sometimes they move so fast that they change from a liquid to a gas. So, solids, they'll expand, and molecules can't move around one another in a solid, and so they'll move back and forth faster. So we're just talking about gases, and when we deal with temperature, we have to deal with temperature where we won't have any negative temperatures that we use. Because if we use these gas laws and we have any temperatures that are negative, sometimes when we do a calculation, it will give us a negative volume. We can't have a negative volume. If you have zero volume, you can't have negative volume. You can have zero pressure, you can't have negative pressure. So what we have to do is we have to find the lowest temperature when you get something down to. And they have theoretically calculated what that's going to be. And that theoretical point that is absolute zero is a minus 273.15 degrees Celsius. So absolute zero in degrees Celsius is a minus 273.15. We could go out further if we wanted to, degrees Celsius. So what you're going to do, I don't know if we'll do 2 labs or 1 lab. We're going to do lab on Thursday or Friday, dealing with pressure and temperature. If you notice in math, when you take the rise over the run, what is that called?
Slope.
Slope. Okay? So what we're going to do is we're going to take the rise over the run and get a constant. Because anywhere along that line, when I take the rise over the run, I'm going to get the same value, same constant. And so that one works a little differently than the constant we came up with for Boyle's law. Boyle's law, we had to take pressure times volume to get the constant. Here, it's a linear relationship right away, and so we just take pressure divided by temperature to get the constant when we get it. But what they do is they'll find the pressure at different temperatures, and then what they'll do is connect all the lines, find where it intersects a zero pressure, where they don't have any motion, and that is found to be at a minus 273. Okay? So that now becomes the starting point of our temperature. So what's the starting point of the Celsius scale? What is it? 0 degrees Celsius. What happens at 0 degrees Celsius? Freezing of water. Okay? So now what they're going to do is they're going to say, we don't want any negatives. We know this is the absolute lowest temperature something can get to theoretically. So that becomes our 0. So this becomes 0 Kelvin. And then everything above it is going to be positive. So in our laws, we have to use Kelvin in which to do find our different values. It has to be in Kelvin. So here's the conversion from Kelvin. If you're given degrees Celsius, which a lot of problems when we do them in class, we have thermometers and they measure it in Celsius. We don't have a Kelvin thermometer. So we always have to convert Celsius to Kelvin. Now you could have a problem that's already converted for you, and that's a possibility. You just have to double check the units. So Kelvin equals Celsius plus 273. If I need to convert back to Celsius, then I subtract 273. So add to find Kelvin, subtract to find Celsius if it's in Kelvin. Okay, so 270. And usually I just use 273 because unless the temperatures are taken out to the 10th or 100th spot, then we won't include the 0.15. If temperatures are taken to the nearest degree, we just subtract or add 273. That's all you need to do. Okay? Now, if it's taken out a little bit further, then you may include that 0.15 in there so that you can take it out a little bit further when you do that. The first law we're going to look at is Charles' law, and then the next law, Gay-Lussac, I'm going to give you both of them all at once. Okay, it says that if we look at volume, how does it relate to temperature? Keeping a couple things constant. We're going to keep two things constant. The amount of gas that we have to begin with has to remain the same throughout the experiment, if we're going to compare volume and temperature. And the volume of the gas. Oh, I got to make a change on this. It didn't record. So if you're to this point, this one's wrong. I made a change earlier, but then I made a copy of it and it didn't show up in copy. So let me change this real quick. Okay. Another thing we need to keep constant is the pressure. So those two things throughout the experiment we're going to keep constant. They're not going to change. What two things will change in the experiment is the Kelvin temperature and the volume. So those two things are going to change. And when they change in the same direction, which means if you double the temperature, volume doubles. If you cut the temperature to be 1/2, the volume will be cut to 1/2. So it's a direct relationship. Boyle's law was an inverse relationship. Okay? Which means when volume was cut in half, pressure doubled. Did you guys notice that on your lab? You guys did your lab. It went from like 10 to 20. Yeah. You had to write numbers down. Or it went from 10 to 5. That those numbers doubled or cut in half, depending upon which one you were looking at. This one, temperature would have to double, which means it would have to change a lot. It wouldn't be like going from 25 degrees Celsius to 50. That's not doubling, because it has to be in Kelvin, and that would not be doubling in Kelvin once we do the conversions. Okay, any questions on Charles' law? It's real simple. It's a rise over run is your slope, kind of like pressure over temperature. Same idea, same concept. Right? We're going to do Gay-Lussac's law as well. The only thing that's different, we switch volume and pressure. So in Charles' law, it says the volume of fixed mass of gas at constant pressure varies directly with the Kelvin temperature. This one says the pressure of a fixed mass, which means we don't change how much gas that we have, and we also don't change the volume. It's going to vary directly with the Kelvin temperature, which means they're going to change in the same way, just like volume and temperature does. So that's Gay-Lussac's law. So again, there's two things we have to keep the same throughout the experiment if we're going to compare those two variables, pressure and temperature. Okay? You have your book open to page 370. If you don't, that's the page we're going to be on. We're going to do sample problem C together. So sample problem C is based upon Charles' law. So we're going to look at sample problem C once you get that one written out. So, by tomorrow, we've done the three laws. Boyle's law, Charles' law, Gay-Lussac's law. We've done problems one of each of those. And then tomorrow you can come in, we'll have you finish up your lab, look at the combined gas law, and then probably spend half hour, you guys just working problems, making sure you're doing right. Okay? if you look in your book, this is the same as sample problem C. We have 3 measurements. We got one, it's a volume. We got 2 temperatures. Okay? So this one is volume versus temperature. Which volume versus temperature would look like this when we're trying to solve it. Okay? So that's the one we're going to have to use to solve this. We're looking for the new volume. V2 would be your new volume. Okay? We're given T1 and T2 because we're given 2 temperatures and we're given the beginning volume. Okay? So what I'm going to do, and I suggest you do this as well, I have students that I would say a third of the students in here, if I ask you to solve for T2, given the initial temperature, the initial volume, and the final volume, a third of the students would get it wrong. Because they don't know how, for some reason, to do the extra step to solve for the denominator, the symbol that would be a denominator. Okay. So this is what we do. We get rid of that by cross-multiplying. You do that with numbers, you cross-multiply, you do it with symbols. So what we'll do is we'll set this up to say V1 times T2 equals V2 times T1. So what we've done, instead of cross-multiplying numbers, we've just done it with symbols. Any questions with that? So now it becomes easier to solve for, because now we don't have to do but one step to solve for our final answer. Okay, so there's our setup. So then now we just have to identify the V1, the T1, the V2, and the T2. So you guys help me identify these. So what's V1? 752. Okay, 752. T1? Okay, so right away what I'm going to do is I'm going to say, it's not 25. I'm not going to make a mistake. Write that in there. It's 298. Right? Because I got to have everything in Kelvin. So I automatically add 273 to all my Celsius. Okay, and I also have a fair number of students that won't do that, especially right away. And they'll put 25 in here. And then they'll put T1 as 25. And the gas laws don't work that way. You have to have it in Kelvin. So it's 298. And then if I'm going to do that, I might as well do the next one too. So it's 298 Kelvin. Next one's 50. I'm not going to use that. That one's going to be 323. I add 50 plus 273 is 323. So I get 323 here. All I need to do is solve for V2. So see, go ahead and set that up to solve for V2 and see what you get.
Is that for Celsius cross
25. 25. So go ahead and solve for V2. A lot of students, not a lot, students will get this wrong, will do it without doing any setup, and they tend to get these temperatures switched around. So instead of taking 752 times 323, they'll take 752 times 298. Just because they're not willing to maybe identify the different temperatures. So hopefully you'll take time to do that, and won't do it in a hurry, because when you do that, you get a lot of the problem wrong when you set it up that way. Okay? Just take a little extra time. That's all you need to do. Okay? So the answer you should come up with for that one, of course, is 815 milliliters. Okay? Last problem we're going to do is sample problem E on page 373. If you notice the volume went up. It makes sense. Temperature goes up, volume goes up. If you did it wrong, it would go back and go, okay, realistically, what I know when temperature goes up, volume goes up. And for some reason my volume went down. It's probably because you had 298 up here, multiply by 752 and 323 below. So you can always catch yourself. You can always double check and go, alright, temperature goes up, volume needs to go up. It's not. What's going wrong? So you go back and look. So that ways you can kind of double check that as well. Okay? So the other one we're going to look at is sample problem E on page 373. Alright? And on that one, we're looking at pressure versus temperature. Alright? So we'll have a P1, a T1, a P2, and a T2. Okay. So again, we've got our setup P1 over T1, final pressure over final temperature. I'm going to cross multiply. So then it becomes pressure 1 times temperature 2 equals pressure 2 times temperature 1. Okay. Go ahead and write down what the pressures and temperatures are. So on that one, go ahead and write down what the pressures and temperatures are.
On this one, same as on E?
Yep. $372. So the temperature is going to go up, not very much. So the pressure is going to go up, but not very much. So we're solving for P2. So divide both sides by T1. So you got your 3. Don't make a mistake when you have them written out. you can go directly down here and go, okay, T2 is 325. And even if you have them written out and you do make a mistake, then I can see you have it written out and I can give you some credit for it. If you don't show that, then I don't know how you're finding your temperatures, how you read. I don't know if you're guessing or not. Here you're not really guessing, you just made a mistake transferring the temperatures over. Okay. And then, so when you do the calculation, it does get a little bit higher, the pressure, and it's 3.27. So again, when you deal with gas laws, temperatures have to be Kelvin. If you're not going to write Kelvin, you're write Celsius, automatically going to be wrong. Okay, they got to be in Kelvin, and that's a common mistake students make. Another common mistake students will make is they're just guessing at what T1 and T2 would be, and they're just kind of guessing, throwing it in there. So I don't want to guess. So, okay, that's all we're going through today. Tomorrow we'll look maybe at what's called combined gas law real quick. And a lot of these are just setups, doing calculations, making sure Celsius is in Kelvin.
What is the label for
It'd be atmospheres. It'd be the same as the pressure. So yeah, the labels will be the same as the initial pressure, volume, or temperature.